So for this, we have an interactive app to talk about it. So let me pull that up real quick. And in this app, what it does is it gives us a way of visualizing the average value of a function and what it actually means. So in this example, the function that's being graphed here is y equals cosine x plus 1 on the interval from x equals 0 to x equals pi over 2. So that's this blue curve. So how does one find the average value of something? More to the point, how do you find the average of anything? It's almost a statistics question. What does average mean that you're doing usually? Yeah. Right, the first step is adding up a bunch of stuff, and what's the second step? Divide by how many things you had, right? And that same notion powers our idea of average value as well, right? That if I want to know what is the average value of this function over the interval from 0 to pi over 2, theoretically what I should do is take every single value that this function takes on from 0 to pi over 2, add up all those values, and divide by how many values we had. But what's the problem with that? Why is that not a practical thing to do? Because there's just too many points, right? In fact, how many values of x are there between 0 and pi over 2? Infinite. In fact, it's a really bad kind of infinity. It's an uncountable infinity, as the math majors will identify with. So there are infinitely many points between 0 and pi over 2, so it doesn't make sense to actually add up all those values and divide by the number we have, because the sum would be infinite, and then we would be dividing by infinity, because that's how many we had. And infinity divided by infinity is one of those cipher quantities that we call indeterminate in calculus. Right? It can mask really any value that it wants to. So we really need some more tool work before we can figure out how to do an average value. But we know how to average a finite set of values. We add up the values and we divide by how many we had, and that's how we begin to speak of the average value of a function. So if I just, for instance, from 0 to pi over 2, if I just take the values of this function at x equals 0, and let's say halfway through my interval x equals pi over 4, I add up those values and I divide by 2, I get an approximation to the average. In this app, that's the value that's shown down here at the bottom center. So if I just take these two values that are shown, in other words, this red height at 0, x equals 0, which happens to be 2, and then I take this height at pi over 4, cosine of pi over 4 is square root of 2 over 2. So square root of 2 over 2 plus 1 is approximately 1.707 or so. And then I average those two values, and my mistake, actually where that's shown, is down here at the bottom. So the approximate average is 1.83. But again, we're missing out on a lot of the behavior of this function if we only look at those two values. So really, to get a better and better approximation for the average value, I need to be choosing more values on the interval from 0 to pi over 2. And that's where in the app we can use this little slider to change the number of intervals. So if instead of 2 intervals, now I go up to using 8 intervals. Now I have these 8 different heights, beginning with 2, but then stepping down. And I'm not going to compute these values, but you can see what they would be. Add up all of those and divide by 8, and I get another approximation, which the app shows you down here at the bottom, 1.697, which is closer to what we would mean by the average value, but it's still not there, because a lot happens in between each of the 8 values that we chose here that we're not capturing in this average. So we keep going. Instead of choosing 8, we end up choosing a bunch more. If I choose 20 values, and I find what the heights of all these little red lines are, add those all up and divide by 20, I get another approximation down here at the bottom. But even this is not good enough, and so we have to keep going and keep going and keep going, choosing more and more and choosing more and more. And just like we always do in calculus, the true average value is found as the limit. The limit of the averages of the values of this function on the interval, divided by the number of samples, I guess, that we took to determine our average. So what does that look like? So based on what you read and what you watched about average value, what do we end up doing in this process of taking a limit? What does the average value become? let me just write it out as a limit, first of all. It's the limit of the sum of the values of our function at a variety of different points. Okay? So the xi's are a sequence. We'll talk more in the second half of our course about sequences, but the xi describes this sequence of x values that we're using to take this average value. So here are the xi's. We might think of x sub 1 as being our first value, x sub 2 as being our second value, and so forth, x3, dot, dot, dot. So I want to add those all up from I equals 1 up to n, where n is the number of samples that I'm taking. So there's the addition part of taking the average. But then, in addition to adding them up, I also have to divide, because it's an average, by the number of samples that I took. So if we forget about the limit portion of this for just a second, this expression, 1 over n times the sum of the values of f, is exactly the average of the finite set of values that we took. But then we want to take this limit. As n goes to infinity, right, we want to take, quote unquote, an infinite number of samples, an infinite number of values, and average them all together. And this would look like a Riemann sum for an integral, except that it's missing something. The Riemann sum for the integral of f on the interval from a to b, or something, has an additional factor in it. It has this delta x, this width of each interval in between, but that's missing from our average value expression. So before we can turn this sum that we have here into a Riemann sum, we need to throw in the delta x. Because once we've thrown in the delta x, then in the limit, this becomes just the integral of the function, f of x, from x equals a to x equals b, where a and b are your upper and lower limits. But we can't just throw in that delta x for free, because then we've changed the value of our limit. So if I throw delta x into my sum, I also have to compensate by taking it back out again. So dividing by delta x on the outside. So I end up with this extra factor. And the problem, n times delta x, is that both n and delta x change as we let n go to infinity. Luckily for us, though, does anyone remember, when we're thinking about Riemann sums for integrals, how do we compute delta x? How do we know how wide each one of these little strips is when we're taking an integral? If my integral goes from x equals a to x equals b, and I happen to be using n subintervals, in the case we're looking at here, n is 20, but n is whatever we need it to be, how do I know how wide each one of those subintervals is? B minus a, so tell me what b minus a is measuring, by the way. Right, it measures the total distance, horizontal distance, between my right endpoint and my left endpoint. Again, there's that subtraction that we also did for finding the area between curves. Right? But then, since we're dividing into n equal subintervals, delta x is b minus a over n. But since delta x and n are both changing as n goes to infinity, in other words, as we have more subintervals, as n increases, the width of each subinterval is decreasing. Delta x is decreasing. But multiply both sides of that equation by n, and we find out that the product of n with delta x is not something that changes as we have more and more subintervals. The product of n times delta x is just b minus a. If I multiply the number of subintervals by the width of each subinterval, I'm going to get the total width that I'm integrating over. And that's fantastic, because that means that in this limit, I have 1 over n delta x. This n delta x that's in my denominator does not change as n goes to infinity. So it doesn't matter that we're taking the limit, and it doesn't matter that n and x are varying because their product is not. In other words, this whole thing in the front goes away, And where I used to have n delta x, now I have just b minus a. And there is an expression for the average value of this function. So this is the secret behind average value, is that there's not much to its computation. It's just the same thing as the integral divided by the width of the interval. Integral divided by interval. It's a bit of a mouthful, but it's pretty straightforward from a computing standpoint. Questions on the setup? I want to return to our pyramid in a second and talk about what this has to do with that, to kind of prime you for the question of the day. But questions on how average value is set up at all? All right, so here's our pyramid once again. We decided in the process of finding the volume of this pyramid that the top line here was y equals 5/12 x. We also decided along the way that if we were to take a slice of this pyramid at some arbitrary value of x, then the width of that slice sorry, not the width of that slice, but the area of that slice was 25 over 36 times x squared, if our slice is taken at x. And then when we computed the volume, we found out that the volume was 50. So for a moment, let's imagine that instead of a pyramid, pyramids are hard, right? Because the width of each one of these cross sections, the area of each one of these cross sections varies as we go from the base to the apex. So instead of a pyramid, let's suppose that we take this object and we sort of smush it in a way that preserves the volume, so the volume stays the same, but we're going to smush it into a rectangular prism instead. Looks like a stick of butter. Ugh. Not the greatest drawing in the world. I do a little better with this in the whiteboard than on an iPad, so bear with me. So imagine that we just smush this into a rectangular prism that has the same height, so the height is still going to be 6. And let's suppose that it has the same volume as the pyramid does. My question is, then what is the area of this base? If this is a rectangular prism with a height of 6 and a volume of 50, what does this area have to be? I heard someone say it.
50 divided by 6.
50 over 6. Thanks, Min. Yeah. Or if you like, 25 over 3. Because after all, the volume of a rectangular prism is just the length times the width times the height. Or if you like, it's the area of the base, because this is a square base, times the height. Area of the base times the height. And if we know that the height is 6 and the volume is 50, then that must mean that the area of the base is 50 over 6. Okay. So now here's a question. What is the average value of this area? The area of an arbitrary slice of our pyramid. Well, how do I set up an integral to find out what this average value is? Give me the average value integral setup. So if I'm looking for the average value of this function, I'm going to integrate this function, right? X squared dx. What are my limits of integration?
0 to 6.
0 to 6. And then to make it an average value, what do I have to do besides that? 1 over b minus a. And here b minus a is 6 minus 0. Right. The average value is 1/6 times the integral 0 to 6 of 25 over 36 x squared. Well, okay. Except that we already did this integral. This integral was 50. Because this integral was exactly the volume of this solid. And therefore, what I'm looking at here is 1/6 of 50. Or 50 over 6, 25 over 3. Well, hey, that's the same thing as we had up there. So this kind of does two things for us. It gives us an interpretation for average value. The average value of the area of one of these cross-sections is exactly the area that a cross-section would have if we took this pyramid and we made it into a rectangular prism of equal area. Sorry, equal volume. Equal volume. And it also gives us some connection between average value and volume here. That even if we have a complicated solid, like a pyramid or like a cone or like one of these things that your group is going to work on in a minute, that if we were to take that solid and make it into a nice solid, all of whose cross-sections had the same area, like that stick of butter over there, then the average value tells us exactly what the area of one of those equal cross-sections will be. So there's a connection. And you have two tasks in your group. The first is to take the solid that's sketched for you on the page, and I'm going to try to project a little better view of those in color on the front screen, just in case the figure is unclear. And to find the volume of that solid by, first of all, taking an arbitrary slice and finding what is the area of that arbitrary slice. That's the second question. The third question is then find the area, find the volume. But then also find the average value of that area and verify that that average value really does give you the area of something that either looks like a stick of butter in this example, or if your cross-sections are circles, it might look like something different. But with your group, try to write something after question 4 about what exactly that average value is telling you about the problem you just did.